Hello everyone, welcome to the communication lab. The aim of the experiment is simulation of pulse code modulation using MATLAB. The pulse code modulation system consists of three steps: sampling, quantizing and encoding. In the sampling process, the message signal is sampled at regular intervals of time. Then these sample values are quantized. A definite finite number of voltage level is assigned to them. Then finally they are encoded. If it is a 3-bit encoder, then each voltage level is being encoded into 3 bits. If it's a 4-bit encoder, each voltage level will be encoded into 4 bits. Let's go to the MATLAB part and implement the sampling process, quantizing process and the encoding process. Here we have the codes for the PCM system. N is the number of bits to be encoded, which here I have taken as 4. So each voltage level is going to be encoded into 4 bits. Fs is the sampling frequency. Here I have taken 10, means the number of samples taken in one period of the message signal. L is the number of levels. So if the number of bits are 4, then the number of levels between the minimum and maximum baseband signal, the message signal, will be 2 raised to the power 4. So that is equal to 16 levels. The first step is to plot the baseband signal. So the time axis is taken from 0 to 4 pi with an interval of 0.01. The message signal is shown by variable m. It is equal to 10 sin x. Subplot and plot are used to display the signal. The second step is to sample the data, sampling process. The time axis is taken from 0 to 4 pi, same time period. Now the intervals are taken with the rate of the sampling frequency. So 2 pi by fs is the interval of these intervals. S is the variable used to signify the sampled output. It is equal to 10 sin x. 10 is the maximum voltage taken here. So to plot or display the discrete data, step function is used. So step x comma s is used. Then title, x label and y label are used for the sample signal, time and amplitude. Next step is the quantization process. Once the sampling data has been done, it is being quantized. The maximum value of the voltage is 10. The minimum value is minus 10, that is minus Vx. The step size is the difference of Vmax and Vmin by L. This is step size. These are the quantization intervals. Then the different levels taken from V minimum to V maximum with D steps is given with the variable amp, that's amplitude. Welcome to the continuation of PCM in this communication lab. Code defines the range of quantized values from V minimum minus D by 2 to V maximum plus D by 2, and code stores that quantized values, those range. Now index Q is the matrix where index stores the index number, Q stores the quantized value. It contains a quantized value. And quantize is the command to quantize the values. S is my sample signal, amplitude is the range of the different levels, code is the variable to store that quantized range. Now this is all in decimal. To make the index as decimal to start from 0, we have this loop, for loop. So L1 is defined as the length of the index, L2 is defined as the length of the queue, and we are using this for loop to start the index from 0. As we know, matrix starts from 1. So we have to do this, and in order to make the quantized values between the levels, defined ranges, we have used this loop. Q is the statement used for display and subplot 313. Stem is used for discrete display. Title, X label, Y label are used for the graph. Now once we have these decimal values, it needs to be converted into binary, and we have used here this encoding process. Decimal to binary is used for conversion from decimal to binary. This is the command that we use it. We store it in the code variable. Index contains the index number, and left MSB is used for just to define that left bit is the most significant bit. So Q is in the form of a matrix. And we wish to have the bits, the binary bits, in form of a row, in the form of a sequence. So to convert the matrix into row, we have used this loop here. And we are storing the sequence of bits in the encoded variable. Once encoded, stores the data. It is used for plotting, and we use the stairs command. The stairs command is used for display of the encoded signal. We have used axis for a better view, title, X label, and Y label. Let's run the program. So this is the PCM output, final output, the display, and we have the figure 1. It just showed the message signal at the top. Next is the sampled output. Third is the quantized signal. So we can see the quantized signal is a little different from the sampled output because it has to take the quantized values only. So this value at 0, value at near 2, and near 6 are different. So you can change the number of bits, and you can change the frequency, sampling frequency, and just see how the things change in your display. We are done with this experiment. If we wish to see the encoded values, then we can go to the command window, and here are the encoded or the PCM output. So we have a 4-bit PCM encoder. So this is 0100 is the code for the first sample. The next sample it is 0110, and subsequently for the other samples like this. If you would like to plot it, then we can have the figure here. This is my PCM output in form of rectangular pulses representing these bits, the sequence of bits here. If I wish to have the quantized output, this was in form of single values given at the sampled instant of time, at the sampling times. If I wish to have this quantized output in form of staircase, then I can use the another graph 414, subplot 414, stairs Q, where Q is the quantized data stored. I had used MXQ for the discrete data to display the discrete data, and here stairs Q and axis has been used to have a clear view of it. So I can in this figure see the staircase approximation or the quantized output of the sample signal. So we end this program here. Thank you.